So now we are going to start today EDC, right? Electronics Device and Circuit. So today I am going to discuss about the semiconductor physics. Tomorrow we will discuss the PN junction diode. Then we will discuss transistor. After transistor we will discuss MOSFET, and that will be our you can say the classes related to your EDC. Now let's start with the semiconductor physics. Now the first question is, let us take you are having a N-type silicon is obtained by doping the silicon at 300 Kelvin. Which type of doping you should introduce to make a silicon N-type? N-type means what? See, basically listen carefully. There are three types of semiconductor. First is intrinsic semiconductor. Second is extrinsic. Only two types you can say, intrinsic and extrinsic semiconductor. Whenever we talk about intrinsic semiconductor, intrinsic means there is no impurity atom is introduced inside that one. That is pure silicon atom. Pure semiconductor material is generally known as what? Intrinsic semiconductor. Now, as you know, and in intrinsic semiconductor, if you are at room temperature, its conductivity is not that much high. Its conductivity is low, right? Its conductivity is low. Now as you increase the temperature, more number of electrons and holes are generated as you increase the temperature, but it is not feasible for us to increase the temperature again and again, right? If you are going, let us take, you are using your laptop and you are having only a semiconductor device into that one, and you want to increase the conductivity of that one, you increase the temperature. Can you operate your device at 400 Kelvin? No. Can you operate that device at 500 Kelvins to get a sufficient amount of, you can say, the conductivity? No. So then what should we do? We will use another approach to get a good conductivity from an intrinsic semiconductor. We will introduce new type of impurities into that one. When you introduce the impurity into that one, that will be converted into extrinsic semiconductor. So intrinsic to extrinsic means what? Intrinsic means pure. We are introducing the impurity atoms into that one, right? Then it will be converted into extrinsic semiconductor. Extrinsic semiconductor, right? So if you want to convert a intrinsic semiconductor into extrinsic semiconductor, we have to introduce the impurity atom into that one. Remember that. Why we are doing the doping? Why we are introducing the impurity atom into that one? Why we are doing so? Because we want to increase the conductivity of that one. Now on the basis of that one, your extrinsic semiconductor are further divided into two types, N-type and P-type semiconductor, right? N-type means what? When you are introducing the pentavalent impurity into that one. N-type means what? When you are introducing pentavalent impurity into that one. Pentavalent means what? Whose outermost shell having 5 electron. So fifth group elements are generally pentavalent atoms, right? Fifth group elements are generally pentavalent impurities, right? We have to introduce the pentavalent impurity to make a N-type semiconductor. So what are the pentavalent impurity? Phosphorus, arsenic, antimony, right? Phosphorus, arsenic and antimony. These are the pentavalent impurity which should be introduced into the pure semiconductor so that it will be converted into N-type semiconductor. So here we are having the four options. So which one? That is phosphorus, right? And if you want to make the P-type semiconductor, it means you have to introduce the trivalent impurity into that one. So trivalent is third group element, aluminium, boron, germanium, aluminium, boron, that group will be your third group, and from that third group we are getting the p-type semiconductor. Inside that one we are having aluminium, boron. So these are the third group elements. So to get a p-type semiconductor, we have to give the impurity atoms from the third group atom, and to make a n-type semiconductor we have to do the impurity of fifth group atom. And here in the option you are seeing another term, that is germanium. What is that? Germanium is just a semiconductor, right? It's just a semiconductor like silicon. And other one like aluminium and boron, that these are the trivalent impurities. Right. So this is all about this one, right? Let's move to the next thing. The doping of boron in silicon results in what? Very good. That will make p-type extrinsic semiconductor. See, this is boron. Can you see? Boron is which group element? Fifth group or third group? Boron is not fifth group, it is a third group element, right? Third group element, right? Not the fifth group, right, Amisha? So it is a third group element, boron. That is the part of aluminium, third group. Third group means its outermost shell has 3 electrons. If you are having a boron like this, its outermost shell has only 3 electrons. So whenever it is making the covalent bond with the silicon, right, it making the covalent bond with the silicon like this, so it is not having one electron to make the covalent bond, so there will be valency of electron that will introduce a hole. So every boron atom which we are introducing inside your semiconductor, that will give you one hole. Hole is a positive type of charge carrier. That's why what we can say, that this is doping of boron in silicon results in a p-type extrinsic semiconductor. Your answer is correct, right? You gave the correct answer. Yes, next question. Now, it is a single crystalline line intrinsic semiconductor at room temperature of 300 Kelvin with effective density of state of holes is twice of that electron. The thermal voltage is 26 millivolt. The Fermi level is shifted from mid-band to where? Right, let's discuss this one. So if you are going for if you are going for NC is the effective density of electron and effective density of hole. Effective density of hole is NV and effective density of electron is NC. Remember that NC and NV. He gives you that NC is equals to NV divided by 2, right? The whole twice that of electron, right? So it means if you are going for NC, that will be NV divided by 2. Now if you are going for the shift in Fermi level, that will be given by EC plus EV divided by 2 minus EFI. This is called as intrinsic Fermi level. That will be equals to KT over Q ln NC over NV. Right, this is the formula for that one. Right, inside this one, this is the new Fermi level and this is your Fermi level of intrinsic. So it will give you the shift in mid-band energy level in intrinsic semiconductor. So this will give you directly shift, and that shift will be equals to KT over Q ln NC over NV. KT over Q is generally denote your thermal voltage at your room temperature, and this is given to you 26 millivolt. Milli means 10 raised to power minus 3 ln NC over NV divided by 2, and that will be 26 into 10 raised to power minus 3 ln of 2. Right, ln of 2 value, if you are, if I write it correctly or not? Okay, NC, yeah, I write it wrongly. NC is equals to NV divided by 2. This is NC, so this is 1 by 2. Yes. So that will be 26 into 10 raised to power minus 3 ln of 0.5. Right, ln of 0.5. Whenever you solve it, you will get it 0.6931 minus 0.6931. That is the value of shift. That is the value of shift in intrinsic Fermi level. Oh, sorry. 0.6931 is the value of ln 0.5. Then multiply also 6 minus 3. So 26 into 0.693 will give you 9 point minus 9.01, right? That is milli electron volt. That will be the shift. 0.91. The answer is D. So whenever is talking about the shift is mainly depend on these things, right? Shift is EC plus EV divided by 2. This is the exact of the middle, minus EFI is intrinsic Fermi level, right? So that means from the middle value it is shifted like this, and that is equals to KT over Q ln NC over NV. So it means the answer is D here, correct. Okay, next question. The Ohm's law of conduction in metal is, what is Ohm's law?
Ohm's law is V directly proportional to I.
V is directly proportional to I. Good. So basically, that is the Ohm's law in your what? That is the Ohm's law in your network theory. Whenever you go for this, what we can say, the EDC, electronics device and circuit, the Ohm's law can be written as, so the first Ohm's law is equals to V is equals to what? I into R, right? This is the Ohm's law. But whenever you go for the electronics, the Ohm's law will change. The J is directly proportional. J is called as current density. That will be directly proportional to the applied electric field. Let us take, you are having a some material, right? Let us take conducting material and you apply the electric field across that one, right? So there will be a current induced inside that one. That current is inducing a current density J. So this is current density J, which is directly proportional to the applied electric field. When you remove the proportionality, J is becomes sigma E, right? This is the Ohm's law, another forms for Ohm's law, right? Ohm's law. Generally in EDC, electronics device and circuit, we will use this form. J is equals to sigma E. So answer for this Ohm's law in conduction in metals is J is equals to sigma E. That is another form which you studied in your network theory, that the current is, oh sorry, voltage is directly proportional to the current, right? V is equals to IR. Now, an n-type sample has length, right? Length of sample is given to you 10 raised to power minus 3. And and the cross-sectional area is given to you 10 raised to power minus 10. Okay. And then has the impurity concentration of atom per second. Let us take impurity concentration. N is equals to 5 into 10 raised to power 20. If mobility of majority carrier mu n is given to you, mobility carrier 0.125. But remember, everything is written here in meter. Right, this is also in atoms per meter cube. Mobility is also given to you meter square per volt second. He is asking about the resistance. We already know the resistance R is equals to rho L by A. Right, and rho can be written as 1 over sigma L by A. Now, we have to calculate this sigma value. That will be equals to nq mu n, right? N is the, let us take, I'm taking that because these are the n-type semiconductor. In n-type we are introducing the electrons, so electron concentration is represented by n. Let us take, this is small n. Q is the charge on one electron, mu n is the mobility of that one. So if I use that to calculate the sigma, n value is given to you 5 into 10 raised to power 20. Charge on electron is 1.6 into 10 raised to power minus 19, and mobility is given to you 0.125. How much we are getting by solving this sigma? Check it and let me know. And then replace that sigma value into that one and calculate the value of resistance. Do it. Yes, how much we are getting?
10 to the power 6. Mm.
Very good. So you already calculated the R value. So R value we are getting 10 to the power 6 ohms, right? And 10 to the power 6 ohm means what? We are getting 1 mega ohm, right? This is the simple just calculation. Now let's just move to this next question. Very good. Now, a semiconductor material is doped with the donor type of impurity with 10 raised to power 5 atom per centimeter. Donor means Nd. Donor means what? Let us talk about this one. There are two types of material, donor and acceptor. Donor means which donate. See, if you are going for n-type semiconductor, in n-type semiconductor we introduce the phosphorus. Phosphorus has 5 electron in outermost cell, so 4 electron make a covalent bond and 1 electron will be free, right? 1 electron will be free. It means that phosphorus atom donate 1 electron to our structure, so that phosphorus atom is generally denoted as donor atom. Whenever someone says your donor atom, it means you have to think that that material is n-type material because 1 electron is donated there. So donor impurity is given to you 10 raised to power 15 atoms per meter cube. If the intrinsic carrier Ni is given to you, that is 10 raised to power 10, then you have to calculate the whole concentration. So always assume that donor concentration will be equals to the number of free electrons there. So now we have to calculate the concentration of phosphorus. As we know, there is a rule that is called as mass action law. What is that? That at thermal equilibrium, N into P is equals to Ni square. Now just replace the value into this one and you will got the answer. Done. What will be the answer?
1 upon 10 to the power 5 centimeter cube.
1 upon 10 to the power?
5 centimeter cube.
That's not. So just we replace n value, that is 10 raised to power 15 into P is equals to Ni square, means 10 raised to power 10 whole square. So this is 10 raised to power 20 divided by 10 raised to power 15. So the P will be 10 raised to power 5. Right, that will be 10 raised to power 5. Very good. B. The concentration of ionized acceptor and donor in a semiconductor are Na and Nd. Na is greater than Nd. Ni is the intrinsic carrier concentration. Then the position of Fermi level with respect to intrinsic level depends on which things? Right. So let's discuss it. Okay. Amisha says A is the answer, right? Na minus Nd. Okay. Let's discuss it. So he says ionized means what? The atoms which already give their electron, or who's having the holes, right? Who give the electron, that is called as ionized electron. So he says that, sorry, ionized atom. He says that ionized acceptor and donor atom in the semiconductor is Na, and Nd. So if Na is greater than Nd, then Ni will be. Let us think about that one. If inside the semiconductor we are having Na acceptor atom and Nd, just 1 second. Okay. So let's discuss it in one by one. So he says Na is the acceptor atom, Nd is the donor atom. Let us take, we introduce Na equals to Nd. What is happen? Na is equals to Nd. So number of electron will be equals to number of holes. If you introduce Na equals to Nd, right, then number of electrons will be equals to number of holes. It means number of electron equals to number of holes. That will make that semiconductor as a intrinsic semiconductor. Now, if your Na value is greater than Nd, then the effective number of holes, in that case, the holes will be greater than the electrons. Then the effective number of holes is how much? That is Na minus Nd. When you introduce them, some electrons and holes are recombined. We will left with only Na minus Nd number of holes with us. So what will be the answer? It means your Fermi level is depending on these two things, Na minus Nd, and this type of semiconductor where we introduce both acceptor and donor impurity, and acceptor impurity is greater than the donor impurity, it means that type of semiconductor generally behave as a p-type semiconductor, and Fermi level, as you already know, in p-type semiconductor, that will be lying near the valence band. So it means that will be depending on that thing, Na minus Nd. Yes, very good, Amisha. Your name is Amisha, right? Amisha, right. Do it. He says that a silicon sample is uniformly doped with 10 raised to power 16 phosphorus atom and 2 into 10 raised to power 16 boron atom. If all the dopants are fully ionized, then the material is, which type of material is this one? Try to solve it. Yes, what will be the answer?
Ten to the power 16 centimeter per centimeter cube P type barrier concentration. B option.
Option B, good. So basically, good. Right, Ishila. So Na uniformly doped with phosphorus atom. Phosphorus is which type of material? Trivalent or pentavalent? Pentavalent, right? It means that is giving you the donor atom. The donor atom is 10 raised to power 16, and boron is trivalent, that is 2 into 10 raised to power 16, right? Per centimeter cube, per centimeter cube. Now, as we observe here, the acceptor atom is greater than the donor atom, and the difference between the acceptor minus donor will give you 10 raised to power 16, right? The difference between these two is 10 raised to power 16. It means that semiconductor will be p-type semiconductor with concentration as, yes, very good, concentration as 10 raised to power 16. So we have to be more focused in these type of questions, right? These are very important for your exam. Sometimes he give you these type of dopings. Yeah, it is also a very good question. He says a semiconductor is uh, irradiated with light such that the carrier are uniformly generated throughout the volume. The semiconductor is n-type with Nd is given to you. The excess electron concentration is steady state is delta n. TP is the generation rate due to that one. Okay, everything is given to you. You have to solve it. Yes, what will be the answer? Let's discuss it also. He says that semiconductor is n-type. It is having the donor impurity atom, that is 10 raised to power 19 per centimeter cube. The excess hole, sorry, not hole, electrons, sorry, excess electron concentration, that is delta n, that will be denoted as 10 raised to power 15 per centimeter cube. And the tau p is the minority carrier lifetime. The generation rate due to radiation. Generation rate due to radiation. See, whenever your semiconductor is in you can say steady state condition, at steady state of what is happening, at which rate your electron and holes are generating, at the same rate they are recombined with each other. So always remember, at steady state the generation rate is always equals to the recombination rate. And generation rate means what? See here, we are having excess means extra. We are having 10 raised to 15 electron extra, and one electron take How much time? 10 microsecond to recombined with a whole, right? To recombine with a whole. So it means how many electrons are generated per second? Currently we are having 10 raised to power 15 electrons, and one electron can have a time of what? 10 microseconds. So what we can say, 10 raised to power 22 electrons and holes pairs are generated per second. That much amount of electron hole pair generated per second per centimeter cube. Then only, because whenever the generation is happening, generation means what? The electrons and holes are both generated at the same time, right? Am I correct or not? uh 10 into 10, yeah, sorry, it is 20 there, right? It is 20. So 10 raised to power 15 divided by 10 microsecond, it means that will be equals to 10 raised to 20 electron hole pair per second per centimeter cube. That much amount of electrons and holes. But remember, at steady state, the generation rate is equals to what? Recombination rate, right? Here it is giving you at steady state the excess means extra electron which is generated. If that much amount of electron is available and one electron can take 10 microsecond to recombine, it means how many electrons are generated per second? The electrons which are generated per second, that will be 10 raised to power 20. Then only these 10 raised to power 15 electron can survive, right? If the generation rate is 10 raised to power 20. The drift velocity of electron in silicon. What is the drift velocity? Isita says B. Yes, Samisha. Isita's answer is D. So drift velocity of electron in silicon is how much? D. Okay, let's discuss it. In the solution, I have two figures that is very important. See here. This is the graph which is very important. You should remember, right? What is that? If you are having the drift velocity on this axis and you are having the electric field on this one, as we already know that drift velocity is directly proportional to applied electric field, and drift velocity is equals to mu times E, if you remember that one. This is the relation. But this relation is only applicable for this region. Can you see? Until this one. until 10 raised to power 3, that is linearly increasing. After that, as you increase the electric field, that will not follow the linear relation, that will go under sublinear relation, and then after 10 raised to power 4, it will get it saturated means constant. If you increase the electric field, now after that drift velocity will not going to increase. The same thing will happen to your mobility, right? Same thing will happen to your mobility. The mobility mu, which is written in that relation, the mobility is remain constant until this 10 raised to power 3. After that, why this is sublinear, and on that one, why that one? Because of this mobility, the mobility is now getting decreased, and after that exponentially decrease there. So that's why what we can say, this one, this portion of VD. Now come to the question, what he says again. So this is very important. The drift velocity of electron in silicon increase linearly with electric field at low value and of electric field, and gradually saturated at higher value of electric field. Very good. D is the correct answer. So that is the graph which you should remember about the drift velocity and the mobility. Next question. A small concentration of minority carrier is injected into a homogeneous semiconductor crystal at one point. The electric field is 10 volt per centimeter is applied across the crystal. This move the minority carrier at a distance 1 centimeter in 20 microsecond. The mobility will be. Do it. I get it. Yes, C is the answer. Okay. Amisa says C and Isita says Z. Sorry, D. Which one is correct? Let us check this. He says small concentration of minority carrier is injected in a homogeneous semiconductor crystal at a point. The electric field E. The E is given to you 10 volt per centimeter, and he tells you that the crystal and the move the minority carrier at a distance 1 centimeter. So we can calculate the drift velocity from that 1 centimeter. 1 centimeter in 20 microseconds. So don't convert that. Remain that into centimeter divided by 20 microsecond means 10 raised to power minus 6. So 10 raised to power 6 divided by 20 centimeter per second will be the drift velocity. Right, Isida? And this drift velocity, that is electric field, we already drive that one. The drift velocity is mu times E. So mu value is Vd, drift velocity over the applied electric field. So Vd value is 10 raised to power 6 divided by 20. And now we are having electric field as 10. So it means that will be 5000 will be the answer, right? Centimeter square per volt second. Then note the D answer. C is the correct answer, right, Anisha? You are correct. Now, this is the question. The intrinsic carrier density at 300 Ni is given to you. Intrinsic carrier concentration 1.5 into 10 raised to power 10. And N-type silicon doped with. N-type means donor impurity is given to you 2.25 into 10 raised to power 15. Electron and hole concentration both you have to calculate. Do it fast. Yes, B option. Amisha says B. Yes. So intrinsic semiconductor Ni is given to you, Nd is given to you. Nd means what? N-type semiconductor donor impurity is given to you. So donor impurity directly equals to N. So N is 2.25 into 10 raised to power 15, right? N means donor atom. Donor means it is giving you directly the electron, right? Donor impurity we are getting from that one. Now N into P is equals to what? Ni square. So the P value is Ni means what? 1.5 into 10 raised to power 10 whole square divided by 2.25 into 10 raised to power 15, right? So from that one we are getting 2.25 in the numerator into 10 raised to power 20 divided by 2.25 into 10 raised to power 15. So if you solve it, you will getting 10 raised to power 5. So C will be the correct answer. C or B? Uh, C will be the correct answer, not B. Right? C is the correct answer. Right, Ishita? Basically, we have to calculate the number of electrons and number of holes. How you are getting B? B is not correct. C is the correct answer because we are getting the number of donor atom. It means that is directly equals to the electron concentration, and by using this mass action law, we will got that the P value, the holes concentration, that is Ni square divided by N. Right? The electron concentration of a sample of non-uniformly doped N-type silicon at 300 Kelvin varies linearly from this. Okay. Assume the situation that the electron are supplied to keep this concentration gradient constant with time. If electron charge is 1.6 into 10 raised to power minus 19 coulomb and diffusion constant dn is equals to 35 centimeter square per second, the current density in the silicon if no electric field is present. Right, do it. So whenever there is a concentration gradient inside the semiconductor, listen this. If there is a number of electrons are high, then gradually the concentration is getting decreased from this point to the another point. It means the electrons are continuously moving and they will generate a type of current, right? This process, whenever the electron move from here to here and they will recombine, right? Or you can say in another way, here the concentration is high, at this position the concentration is low, so electrons or any type of charge carrier which is always go from the higher concentration to lower concentration so that the concentration remain constant. But if you are continuously supplying the electron from this side, that concentration gradient remain there, right? If the concentration is gradient it remain there, it means electrons is always going from here to the higher concentration to the lower concentration. It means they are contributing a one type of current there. That current is generally known as diffusion current, and that diffusion current due to electron is given by what? Q times dn times dn over dx. This dn over dx is generally represent what? The concentration gradient. Dn represents the diffusion constant. Now we will try to find this current. So that current is Jn is equals to, how much is the charge on a one electron? Can anyone let me know? Yes, charge on one electron. That is 1.6 into 10 raised to power minus 19. Then dn is given to you 35. And now the concentration gradient. The concentration gradient is how much? He says that at x equals to 0 we are having 10 raised to power 17, and at x equals to 2 we are having 6 into 10 raised to power. So I am taking 6 into 10 raised to power 16 minus 10 raised to power 17 divided by 2 minus 1, but this is in micrometer. 2 minus 0, not 1, and that will be 10 raised to power minus 6. Right. So you have to solve it completely. And when you are solving that one, yes, very good decision. Whenever you solve this one complete equation, you will got that Jn is equals to 35 into 1.6 into that 10 raised to power 6 will come with this one, that will be 10 raised to power 13, and 6 minus 10 will give you minus 4 into 10 raised to power 16 divided by 2. Right, minus is there. So it will be minus 120, because there is only one option which is with minus. So answer is D here. Minus 120 ampere per centimeter square. That will be the answer. So this is called as diffusion process, right? Whenever at one position concentration is high and other position concentration is low, the electron or the charge carrier always move from higher concentration to lower concentration so that the concentration become constant. That process is called as diffusion. And remember, diffusion is a natural process, right? You cannot create that one. Okay. The resistivity of a uniformly doped n-type silicon sample is this one. If the mobility of electron is that one, charge on one electron is that one, then we have to calculate the ND. Yes, do it. From this resistivity, first calculate the conductivity, then apply the conductivity formula. Conductivity is NQ mu n, and from that one you will get the N value. Right? From this resistivity, first convert that into conductivity. Yes. Option B. Okay. Let's discuss it. The resistivity of a uniform depth, okay, a row is given to you 0.5 ohm centimeter, right? The conductivity sigma is 1 over 0.5, that is equals to 2. And as we know, conductivity is n q mu n. So n we have to calculate sigma by q into mu, and sigma is the conductivity. Q is 1.6 into 10 raised to power minus 19, and mu n is the mobility. Is that given to you? Yes, 1250. So from that one, if I solve, what we are getting, that is 1 into 10 raised to power 16. The B is the correct answer. 1 into 10 raised to power 16 per centimeter cube. Yes, B is the correct answer for this one. The longest wavelength that can be absorbed by silicon, which is having a band gap, right? Easy band gap is given to you 1.12 electron volt, and at this band gap it is absorbed 1.1 micrometer. If the longest wavelength that can be absorbed by another material is that one, the band gap of that material, see, listen carefully. If this is here, this is the band gap of this material. If one electron is here, light is incident, then it will go to the conduction band. So it is required certain amount of energy. That energy Eg, that is energy is required equals to Eg, band gap of that one. And that should be equals to Hc over lambda. So from that one, Eg is direct inversely proportional to the lambda. It means Eg1 divided by EZ2 is equals to what? Lambda 2 divided by lambda 1. Right, so directly we will replace the value, that is 1.12 divided by EZ2. We have to calculate lambda 2. Lambda 2 value, the wavelength is 0.87 divided by 1.12. So from that one we will calculate the EZ2. The EG2 will be equals to what? 1.425, right? From this relation, EG2 is 1.416, something like that. So answer is A, right? Okay, that's it from this part. So solve the rest of the question by yourself. And in the next class, we will start with the diode part, right? PN junction. So just revise that PN junction before come to the next class. Okay, then see you too. See you